Pop the hood of a 1985 Chevrolet Monte Carlo, and you're greeted by a straightforward sight: a cast iron engine, fully exposed and ready to be worked on. A skilled backyard mechanic could pull the heads, swap out the gaskets, bore the cylinders, and get that car running for another 200,000 miles without breaking a sweat. The tools needed fit neatly in a standard toolbox, and all the knowledge required could be found in a book borrowed from the local library. Open the hood of any 2026 vehicle, and the picture looks entirely different. You're met with a maze of plastic covers concealing a turbocharged aluminum engine crammed tightly into the engine bay. And if that engine overheats even once, your mechanic won't offer a repair. Instead, he'll slide a $6,000 estimate, suggesting you start thinking about a new vehicle. This isn't your imagination. The old iron block engines your grandfather knew were built to endure. What sits under your hood today, however, was engineered to survive just long enough to outlast the warranty, then fail right on cue. Every major American automaker made the switch to aluminum engines. They marketed it as a weight-saving measure, calling it a fuel efficiency breakthrough, but in reality, it's an engineering trap. Today, we pull back the curtain on the material switch. We examine the spark plug disaster Ford quietly engineered into its best-selling truck, the timing chain tucked away somewhere no ordinary mechanic can reach, and the cracking heads they quietly address through a vague customer satisfaction program. We share why your aluminum engine was never truly meant to be repaired. Before we move forward, do like and subscribe to keep watching such stories. Now let's lift the hood on the lightweight lie. Number 1. The real reason aluminum took over. The rise of aluminum engines did not begin in a laboratory driven by pure engineering curiosity. It began in government offices and regulatory frameworks. In 1975, fuel economy standards were introduced, and over the decades they tightened like a slowly closing vise. Manufacturers were forced to squeeze more miles out of every drop of fuel. That pressure changed everything. Engineers were no longer just building engines for power and longevity. They were building engines to pass standardized tests under controlled conditions. Weight became the easiest target. Every kilogram removed from a vehicle translated into measurable gains in fuel efficiency. Aluminum, being roughly one-third the density of cast iron, offered an immediate advantage. On paper, the math was irresistible. Reduce engine weight, improve efficiency, meet regulations, avoid penalties. The industry pivoted, and by the early 2000s, aluminum engines became the norm rather than the exception. Number 2. The hidden cost of thermal expansion. Engines live in a world of extreme temperature swings: cold starts, scorching combustion cycles, rapid cooling. Materials inside an engine must expand and contract constantly without losing their shape or integrity. Cast iron behaves like a disciplined soldier. It expands slowly, predictably, and returns to form without drama. Aluminum behaves more like a restless traveler. It expands faster, contracts faster, and reacts more aggressively to temperature changes. This difference matters more than it seems. Every heating cycle stresses gaskets, seals, and internal coatings. Over time, that stress accumulates. Components that once fit perfectly begin to drift out of alignment. In an aluminum engine, tolerances are tighter and margins are thinner. A small overheating event that an iron engine might shrug off can permanently distort aluminum components. Once that distortion happens, repair becomes difficult or even impossible. Number 3. The disappearing art of engine rebuilding. There was a time when engines were not disposable. They were rebuilt. Machine shops thrived on resurfacing cylinder heads, boring cylinders, and fitting oversized pistons. A worn engine was not the end of the road. It was the beginning of a second life. Aluminum engines changed that equation. Many modern designs use specialized coatings instead of traditional iron sleeves. These coatings are incredibly thin and require precise manufacturing processes that cannot be easily replicated in local machine shops. When these surfaces wear or fail, rebuilding is often not economically viable. The engine block becomes a sealed unit rather than a serviceable component. Replacement becomes the default solution. This shift quietly dismantled an entire ecosystem of repair. The local machine shop, once a cornerstone of automotive culture, began to fade. Number 4. When efficiency meets fragility. Aluminum conducts heat better than iron. That sounds like an advantage, and in many ways it is. Efficient heat dissipation allows engines to run at optimal temperatures under normal conditions. But that same property becomes a weakness when something goes wrong. Cooling systems in modern cars are more complex than ever. Plastic components, electronic sensors, and tightly integrated designs create multiple potential points of failure. When a cooling system fails, the engine temperature can spike. Aluminum components respond immediately, expanding and warping under stress. Unlike iron, which can tolerate brief excursions into high temperatures, aluminum often cannot recover. Number 5. The cylinder head problem. Cylinder heads are where combustion happens. They endure the highest temperatures and pressures in the engine. In older designs, cast iron heads provided a robust and forgiving surface. Modern engines almost universally use aluminum cylinder heads. They are lighter and more efficient, but they are also more sensitive. When exposed to excessive heat, aluminum heads can warp beyond repair. In the past, a warped head could often be resurfaced. The process was straightforward and relatively inexpensive. With aluminum, the margin for correction is much smaller. Once the material moves beyond a certain point, it cannot be restored to its original specifications. This turns what used to be a manageable repair into a costly replacement. Number 6. The domino effect of modern design. Aluminum engines do not exist in isolation. They are part of a larger system that includes turbochargers, direct injection, and advanced emissions controls. Each of these technologies adds efficiency, but also complexity. Turbochargers increase pressure and temperature inside the engine. Direct injection improves fuel delivery but introduces new maintenance challenges. Together, they push aluminum engines closer to their limits. When everything works perfectly, the result is impressive performance and efficiency. When something fails, the consequences escalate quickly. Number 7. The economics behind the shift. It is easy to assume that manufacturers simply made a technical decision. In reality, economics played a major role. Aluminum engines are often cheaper to produce at scale due to casting efficiencies and reduced material costs in certain contexts. More importantly, they align with a business model that prioritizes new vehicle sales. An engine that is difficult to repair encourages replacement rather than restoration. This creates a cycle where consumers are more likely to purchase a new vehicle when faced with major repairs. Number 8. When maintenance becomes a minefield. Routine maintenance used to feel predictable, almost ritualistic. Oil changes, spark plugs, timing chains. Each task had a rhythm, a cost, and a clear expectation. Aluminum engines disrupted that rhythm in subtle but expensive ways. Spark plugs are a perfect example. In older iron engines, they threaded into durable material that could handle repeated removal and installation. The process was simple and mistakes were rarely catastrophic. In aluminum engines, the threads themselves are more delicate. Heat cycles expand and contract the metal, tightening the grip on spark plugs over time. When removal is attempted, the risk of stripping threads or snapping components increases dramatically. What was once a routine service can spiral into a costly repair. Number 9. The timing chain trap. The timing chain is the silent conductor of the engine's orchestra. It ensures that valves and pistons move in perfect synchronization. If it fails, the engine does not simply stop. It destroys itself internally. Older engines placed the timing chain at the front, behind a simple cover. Access was straightforward. Replacement, while not trivial, was manageable. Modern aluminum engines often hide the timing chain in places that seem deliberately inconvenient. In some designs, it sits at the rear of the engine, pressed against the firewall. Reaching it requires removing major components or even extracting the entire engine. This transforms a maintenance job into a major operation. The cost is driven not by the chain itself, but by the labor required to access it. What should be a few hours becomes a full day or multi-day procedure. Number 10. Turbocharging and the vanishing margin for error. Turbochargers are like adrenaline injections for engines. They boost power by forcing more air into the combustion chamber, allowing smaller engines to perform like larger ones. But this added performance comes at a price. Turbocharged engines operate at higher temperatures and pressures. Aluminum components, already sensitive to heat, are pushed even closer to their limits. The margin for error shrinks. Oil quality becomes critical. Cooling systems must function perfectly. Even minor neglect can accelerate wear and trigger failures. Turbocharging also introduces additional components that can fail. Bearings, seals, and intercoolers add complexity. Each part is another potential weak link in an already stressed system. Number 11. Direct injection and the carbon problem. Direct injection was introduced as a way to improve fuel efficiency and performance. Instead of spraying fuel into the intake manifold, it delivers fuel directly into the combustion chamber. This approach has clear advantages, but it also creates a hidden issue. In traditional engines, fuel passing over the intake valves helped keep them clean. With direct injection, that cleaning effect disappears. Oil vapors from the crankcase ventilation system begin to accumulate on the valves. Over time, these deposits harden into carbon buildup. Airflow is restricted, performance drops, and misfires can occur. Cleaning this buildup requires specialized procedures. It is not part of standard maintenance schedules, yet it becomes necessary over time. Owners often discover the issue only after symptoms appear. Number 12. Cooling systems on a tightrope. Modern cooling systems are intricate networks of hoses, pumps, sensors, and reservoirs. Many of these components are made from plastic to reduce weight and cost. Plastic works well under normal conditions, but it degrades over time. Heat cycles cause it to become brittle. Small cracks can develop, leading to leaks or sudden failures. In an aluminum engine, the cooling system is not just important, it is critical. There is little tolerance for overheating. A minor leak that might have been manageable in an older engine can quickly escalate into severe damage. Temperature gauges and warning systems often provide limited notice. By the time a problem is detected, the engine may already be experiencing harmful stress. What drivers can do to stay ahead. Owning a modern aluminum engine does not guarantee problems. It simply requires a different approach to maintenance and awareness. Cooling systems should be inspected regularly. Coolant quality matters more than ever, as degraded fluid can accelerate corrosion in aluminum components. Small leaks should never be ignored. Oil changes should be performed more frequently than the maximum intervals suggested by manufacturers, especially in turbocharged engines. Clean oil helps manage heat and reduces wear on critical components. Attention to early warning signs is crucial. Unusual noises, temperature fluctuations, or performance changes should be addressed immediately. Delaying action can turn minor issues into major failures. Choosing the right vehicle also plays a role. Some engines are better designed than others, with improved materials and more serviceable layouts. The truth behind the lightweight lie. The shift to aluminum engines was not a deception in the traditional sense. The benefits are real. Lighter engines improve fuel efficiency and reduce emissions. They enable modern vehicles to deliver impressive performance while meeting strict regulations. The lie is not in the material itself, it is in the incomplete story. The trade-offs were never emphasized. The reduced tolerance for heat, the increased complexity, and the higher repair costs were not part of the sales pitch. What drivers received was a new kind of engine, one that excels in controlled conditions but demands careful maintenance in the real world. Aluminum engines are not villains. They are tools shaped by the priorities of an industry navigating regulation, competition, and consumer demand. But like any tool, they come with limitations. Understanding those limitations is the difference between being caught off guard and staying in control. If this breakdown helped uncover what is really happening under the hood, make sure to like and subscribe to the channel for more deep dives like this.